Hello, so this video here is about this feature called concavity, and this is a characteristic of how a function or how a curve bends. So algebra does not handle this very well. You really need calculus to understand concavity of the graph. And then also something that sounds like the first derivative test. Instead, this is a test that it's going to find mins and maxes just like the first derivative test, but it's going to use the second derivative. In other words, it's going to use this idea of concavity to locate high points and low points to the graph. So first order of business is to talk about this thing that is called concavity. And there are two types of concavity that you can get here. So the assumption first here is that the function is a smooth one, right? So it's differentiable. And then there are two terms that we talk about. So a graph can be concave upward or it can be concave downward. So we're going to call a graph concave upward if the slope is increasing. So this is a tricky thing because the thing that we're talking about that's increasing isn't necessarily the function, but it's f prime, so it's the slope of the function. And so the opposite of concave upward would be concave downward. The slope here is decreasing. So similar to the other videos, I'm going to take just one of these and illustrate it graphically, just to make sure that we understand what it really means. So here's a picture. I think I'll just pick on B. I'll just use B and diagram that. So here we go. So this will be the definition of concave downward, right? Talking about this situation. So most people have an intuitive sense of what these things mean. So this is the graph of f. So concave downward informally means that if you look at this part of the graph, if you were to dump water on the graph, it's going to bead right off the graph, right? So it's really just curving downward like that. But you have to look carefully at this definition. So it says f prime as a slope, right? F prime is decreasing. So you really have to think of this thing as a function going from left to right. So if you think about the slope, I'm going to put one slope right about here, right? And then I'll put another one here, and then another one off to the right. So what you really have to do is to envision the slope, or f prime, as a function, right, going from left to right. And you can see that the slope starts positive, right, that's how it starts, and then eventually it becomes 0, and then finally at this last little diagram it becomes negative. So if you think of the slope as a function, it begins positive, 0, and negative. So one word that would describe what is f prime doing, it's decreasing, right? It's getting smaller. So if you look at the definition, it's really what the slope is doing as a function, and it gives you a characteristic of the original function f. So if you look at the blue graph, we would call that graph concave downward because the slope here as a function is decreasing. So a very similar type of thing you can do for diagram A. So I'll let you just think about that. So some critical things here, something that you might think about is an observation that is similar to the previous section. And this is where you start to make connections. So this is really important. So if you remember in the last lesson, the important observation there is that if you want to see where a function is rising or falling, right, if you want to see where f is increasing or decreasing, then you look at the sign of the derivative, right, whether it's positive or negative. So the important thing to understand here is if you care where f is rising or falling, you have to look at the sign of its derivative. So the connection here is f here and then f prime. So if you look at the definition of concavity, this really isn't about where f is rising or falling, it's about where f prime is rising or falling. So if we just make a modification here on this observation, we don't really want f here, but we want f prime. Okay? So to see where f prime is rising or falling, because it's going to fit this definition here, then you would have to look at the sign of this derivative, right? So the derivative of f prime, so instead of looking at this here, we would look at f double prime. So we're using the old information that we've talked about, but instead of seeing where f is rising or falling, it's really the f prime that's important. So connecting the definition of concavity to the old stuff leads directly to a quick way where you could figure out where a graph is concave upward or downward. And so here it is. So this is the test for concavity. So it uses, no surprise, the second derivative because we just made that connection. So if the second derivative is positive on an interval, then that means the function, the original f, is concave upward there. So I'm just going to use that abbreviation, CC upward. And so just like we see a lot in mathematics, once you have one statement, you can change a couple of things around and you'll have the opposite scenario. So if the second derivative is negative on an interval, then that means the function is concave downward. So we're going to see lots of examples where graphs are neither concave upward nor concave downward, but a combination of both, right? So a lot of graphs will have ups and downs and they twist and turn in different ways, so they'll have just a variation of concave upward and concave downward. So one more thing to talk about here, and then we'll look at an example, because this leads directly into changes in concavity, is something we call in mathematics an inflection point, or a point of inflection. So first thing we notice here is that the point is literally an x and a y, right? So it's c followed by f of c. So this is a point that is on the graph of a function. So we're going to call this point a point of inflection if it illustrates a concavity change. So if you go from concave upward to concave downward, or vice versa, from downward to upward. And the second condition here is that the tangent line must exist. So really, an informal way of understanding this is that the graph must be smooth at that point. So if we more or less have a smooth graph and the concavity changes, then we call this location a point of inflection. So now it's time to look at an example of concavity, and then we'll get to our main result about second derivatives. So this example I had in an earlier video where we found highs and lows. So this time we're going to do something different. We're going to look at the concavity of the graph. And while we're here, we might as well just talk about the inflection points as well. So we're going to go back to this example, but look at different features. So here we go. We have h of x, this function. Okay, that function there. So we're going to look at concavity here. So that means we're not going to look at the first derivative, but we're going to look at the second. And we're going to examine the sign chart of h double prime. And then that will tell us where the graph is concave upward or downward. So h prime here will be pretty simple, 3x squared, and then minus 3x. Okay, so we're not going to stop here, we're going to go one more. So let's find h double prime. So again, the power rule and some of the various other ones, so this will be 6x minus 3. So we're going to do a similar thing here, and we're going to set this equal to 0. And then this is not going to give us a critical number, but it's going to give us a possible point of inflection. So we have 6x minus 3 equaling 0. And so if you solve for x here, it's going to be 1/2. So x equals 0.5, 1/2. And so this here, we don't know for sure if it's going to show a change in concavity, but it could. So I'm going to call this a possible point of inflection. Nice little abbreviation there, PPOI. So this is going to act like our critical numbers for the first derivative, in that we can put this on the number line and then observe the sign of h double prime. So I think I can get rid of some of this here. And so here's our number line, and this is why I label it, because it's good to know what you're looking at. So this is h double prime. So really, right here, 6x minus 3 is our second derivative. So 1/2 is going to be like our partition number, and we're going to check both sides of 1/2. So the left-hand side of 1/2, a good number to check would be 0. So if you plug 0 into 6x minus 3, it is a negative number. Anything to the right of 1/2, like the number 10, if you put 10 in here, you get 60 minus 3. That's very positive. So it's a very nice test. And remember, going back to our earlier result, so I'll just put this up here so we can see it, right? It is the sign of the second derivative that tells you concave up or concave down. So you can see we have downward concavity here, upward concavity there. So I'm just going to label it here. We have concave downward here, and here we have concave upward. So it's customary here to write these in interval notation, and because this is a polynomial and we have a nice smooth function, this will most certainly be an inflection point because we have that nice smooth change in concavity. So I'll summarize by writing down this information. So concave upward, right, that's going to be to the right of 1/2. So it'll be 1/2 positive infinity. And then we're going to have concave downward to the left of 1/2. So negative infinity to positive 1/2. So these are the intervals where the graph has concave upward and concave downward. And then we will certainly have an inflection point at 1/2. So we have a point of inflection when x equals 1/2. So naturally, you could find the y value, right? Take 1/2 and then into this function, and that will give you the y coordinate of the point of inflection. But this more or less gives you all the information that you need to understand the graph. So as is typical, it's very good to look at just the graph of h, because we looked at this graph earlier with highs and lows, but now we're looking at a totally different information. So 1/2 is that very important place where everything changes. So I'll just highlight, if you can't see, right, this is where 1 is. So 1/2 is going to be right about in the middle, and if you find that spot on the graph, right, I'll put a little dot. So this is where the concavity in the graph changes. So you can see to the left of this dot, that's the part of the graph that won't hold the water, right? So it's concave downward here. And then as you pass 1/2 to the right of 1/2, you can see the graph is now concave upward. And then this point, it looks like it's about 0.5 and maybe 1.75 for the y coordinate. This would be the inflection point. And as we mentioned earlier in the definition, it has to be smooth there, and the graph is smooth. If you were to put a tangent line in here, it's sort of an interesting one, so just for kicks, right? So you can put the tangent line in there, and you can see it's unusual because it cuts right through the graph, and that's very typical because you have a change in concavity. So this is just a complete analysis of how the curve bends. And as I mentioned earlier, this is not something that algebra is really good at, but calculus will study or give you an interesting perspective on how the curve is going to bend. So this video has one more main result, and then we'll look at an example to make sure that that result makes sense. And fair warning here, this is a pretty hard thing to understand if we don't interpret everything really carefully. And so this is called the second derivative test. So as I mentioned earlier, it does the same stuff as the first derivative test. So it is going to identify relative extreme values, highs and lows, but it does so in a very, very different way. So if we read the test here, we have a critical number, right? X equals c is critical. And again, I'm going to let you read half of the test. I'm just going to really interpret very carefully 1/2. So this is saying if the second derivative at c is positive, then that means f of c is going to correspond to a low point in the graph. So we have to interpret what this means. So first we know that x equals c is a critical number, and then this is saying that if you put that critical number into the second derivative, then you're going to get something positive. So we already know that a positive sign on a second derivative indicates that the graph is going to be concave upward. So this is really telling us we have a concave upward graph and we have a critical number, and then what does that mean? So as usual, a graph will explain everything. So here's your function, and here's c. So you can see f prime of c is 0. So just do a horizontal tangent just like that. And then the important part of this statement, f double prime of c is positive, and that really means that the graph locally, right, just in a small vicinity is concave upward. So if you look just locally around c, the graph is concave upward, and then you can think about the conclusion that you can make here, that this would have to be a valley in the graph, right? So this part of the statement makes sense. It would have to be a relative min. And so I think the reason this is a tough test to use is because you're taking the critical number from the first derivative, and then you're actually plugging it into the second. And then you observe the sign of that number, because that tells you about concavity, and then that's going to classify the extreme value that you're talking about. So once you associate this graph with the first statement, statement A, you can again just invert this graph, and you're going to get statement B. So we will finish off this video by looking at the same example, right? So we've already talked about this one, but we're going to look through the lens of the second derivative test. So we're going to try to locate the high points and low points, which we already did in a previous video, but the mechanics here are going to look very different. So I'm going to move this over here so I have a little bit of room. So this is the function here. I'm going to just write down the derivative. It should be pretty quick because we already had this on the board. So it'll be 3x squared minus 3x. So what we do here is we might as well find the critical numbers. So we're going to write 3x squared minus 3x equals 0 and factor out a 3x. So we have this result. So only 0 and 1 are going to work here. So these are numbers that you have to hold on to. They are the critical numbers, right? So they're going to lead to the possible mins and maxes. Okay, so what we do here now is to also find h double prime. So I would continue exactly where you left off, right? To use this form of h prime, and then you can find the second derivative. So h double prime, if our eyes are looking here, will be 6x and then minus 3. So we're going to just work with this here, and we're not going to work with concavity here, so we're not going to set this to 0 or anything like that. So I'll flash this up here again, and just to repeat, the reason this test is tough is you have to take these numbers that come from h prime and then insert them into h double prime. And then based on the sign, you can tell if you have a min or a max. So here we go. We're using h double prime and treating it as a function. And so we're going to plug both of these numbers in, 0 and 1. So we're going to put in 0 and then also 1. So if you put 0 into this function, you get a negative 3, and that is a negative number. And if you put 1 in here, you get 6 minus 3. So that's positive 3, and that's positive. Okay, so this information gives us everything we need about classifying these critical numbers, right? Which one's a min and which one's a max. So if we look, for example, at this statement here, I'll underscore it. This is telling us that at 0, the graph of h is locally concave downward. So if you think about a concave downward graph, that's going to correspond to a high point in the graph. So at 0, right, we're going to have a max. So you could just write yourself a little note here. 0 is going to correspond to a maximum value. So now if you look at this statement, this is telling us when x is 1, this graph is going to be locally concave upward. So we think in our brain something like this. So if we have a concave upward, this is going to be a minimum value, and that's speaking to x equals 1. So the other piece of this is 1, right? We're going to think a low point to the graph. So once we have this information, then you can go back to your function, figure out your y coordinates. But the second derivative test is already done here because it allows you to classify the critical numbers that you get by inserting them into the second derivative. So then to wrap up, right, we have a maximum at 0, and then we have a minimum at 1. So this is like our earlier work where you put 0 into the original function, right, and then you can calculate the output. So we have a maximum there, and then a minimum is going to be at 1, and this is 1.5. So this stuff is the same as what we would normally do. This is the novelty here. And so lastly, I'll just put up the graph that we've already seen, right, just to confirm that we're correct. And you can see in the graph at 0, 2, this little spot here that most certainly appears to be a maximum to the graph, and then at 1, that's where the valley is. So right at 1.5, that occurs right there. So that's really what the second derivative test looks like. You have to gather your critical numbers from the first derivative and then put them into the second derivative, and then note that the value that comes out is going to speak to the concavity of the graph. And if you know the concavity of the graph, then you can tell if it's a high point or a low point.